Swayam Prabha. Digital India. Educated India.
Okay, so they all asked me to wish special Happy New Year to everybody who came in later. Happy New Year, everybody. So what I thought, I think yesterday we were having this discussion, we'll go backtrack a little bit. Let me see. Well, I haven't set anything up yet. Let me save the file first. Okay. So yesterday we saw we saw the roof joist, I think, or skip joist problem, and I thought, let's say you have the building, whether it's concrete or steel, so you have a concrete girder and you have several, let's say you have 4 equally spaced, and the girder, whatever support it is, simply supported, let's say, you can change, we'll keep for the class purposes, and then you have the building here, the room here. So, and an explosive, something like this. So, let's say here you had the explosive. So, or even you could have pressures, even if it's not internal, let's say external, we have used the incident pressure or P side on. So, the joist itself is going to be designed for a tributary area pressure this way. So, this is your, so joist design is for PI and TD, it's PI, again note that, for PI and TD, and tributary area. So, when we come to the girder itself, the girder will feel the reactions. So, let's say this is 1, 2, 3 and 4. So, the girder is designed for dynamic reactions. So, how do you design the girder? So, let's take a brief, I took a brief stab at it yesterday afternoon. I was trying to see if there's a way we could do that, and I came up with the best response. Again, our limitation here is use non-lim. There could be more sophisticated programs, and even in nonlinear, I think there is a way you can input the reactions as a function of time. But so here is what I did from the skip joist problem, or just simply call it the joist problem or the beam problem. The parameters or the analysis parameters that we came up with were the following. We had the elastic equivalent stiffness was 27.9. So, these are all, let us say you calculate first kips per inch, and the mass equivalent mass was 34.4 pound, or the weight is mass times your gravity. So, this comes to 13.292 kips. The reflected pressure was 4.52 psi, and the duration was 24.5 milliseconds, and the area. So, in this case we had this tributary width was 6 inches, this is 30 feet, 6 feet, sorry, 6 feet and 30 feet. So, the tributary area was 30 and 6, which is 25,920 inches square, and Rn, this was for the capacity of the joist in flexure. We are assuming that a lot of all the failures are in flexure. So, this was 23.8 kips. So, given this, what I did was use nonlinear, and I have those parameters here. Hopefully, they are all set. Yeah. So, you can you see that, or I don't know if this no. So, anyway, you know, okay, one thing I wanted to mention here was the value we have been inputting as 0.02 for, but it is 2. It is percentage itself, the input should be there. So, especially in impulsive loading, there is a certain amount of dissipation. Whether it is important or not is not, we take the peak values for design purposes, but so make sure you are giving, otherwise you will not see any dissipation, it will just be elastic. So, when I input here, I am inputting as 2. So, that is one error I just wanted to point out that I had mentioned earlier. So, the blast load, okay, it does not, for some reason it does not store the loading, which is okay. So, the pulse duration was 24 point. The only problem with nonlinear, well, it is developed by one person, so it can be a little annoying is if you put something wrong, what happens? It kicks you out, right? So, save your files, and at least you get most of it, and the maximum is 0.00452. So, that is 4.52 psi, and it stores tributary area, but not the other. So, the tributary area is 25,920, and the scale factor now we have it as 1. If you want dynamic reactions as a function of time, there is a limitation, it does not go beyond, especially you can't change this for some reason, at least in my case I am not able to change subdivisions per millisecond. You start putting 5,000 milliseconds and then it is looking at 50,000 sub steps, and then it crashes. So, I was able to go up to 3,000, but for now then I realized we do not really need all that. If you there is a way to do without it. So, you have this function, then when you use it, so let's run that, and so what we get out of this is the natural time period is 221 milliseconds. I'm just cross checking, and then the dynamic reaction is 1.731. So what I did here was go into this file, and then you're interested in, so here if I take it to 33,000 milliseconds or 3 seconds, you'll see there's actually a gradual decrease. Here also you can see it's going slowly dissipating. So the thing of interest was maybe the first cycle. I tried outputting it into Excel. There is a way you can output it into Excel. So you can put that into the Excel file, and then it's for some reason not able to pull in data from, you can manually enter it, but there may be other workarounds. So for now what I did, and it should work for design purposes, is the sinusoidal wave. I see that it is, so let me go back here, and so from nonlinear what I get is delta dynamic equal to 1.739 inches. The time period Tn is 221 milliseconds, and then the dynamic reaction is, so this is your reaction R of T. So you have your force K, M, and then you're applying P of T. So you have this dynamic force. Basically we are doing Kx, it's not the reaction itself. This is this, I've equated these two to be the same. So what I get is a approximation that is, the period is there. So this is 0, 70, and at 140 back to 0, and the peak value here is, so let's go and look at that. So the peak value here is about 20 at 26.2 at 0.07 seconds. You're not able to, if you're not able to read that, that is 70 milliseconds, 26.2 kips, and it goes back to 0 at about 1. And there is also, if you see, there is a rebound effect also. So anyway, we won't focus on that for now. We'll just get to the, so this would be 70, and if you have other ideas, let me know. So this was 26.2 kips, and here at 70 milliseconds. Then so this would be, now when we go to the girder, the loading on the girder is the reaction on from the beams from the skip joists. So let's start with the assumption that the f, so let's call this f of x, or R1, R, let's say joist, Rj of t. So assumption is the reaction on the joist is half on each girder, and there are 4 joists. So the loading on the girder can be taken to be the same thing, because we can input a triangular part quite easily. So the loading, say P on the girder, as a function of time going to 70 and 140. So, the value here is Rj of t divided by 2 multiplied by 4. So, we have this as 26.2 multiplied by 2 eventually. So, this is 53.4 kips, right? You agree with me so far? If you have an alternate approach, let me know. These are some things. So, then we go over here, then we come to, no, I do not want to quit. Okay. So, let us come back to the girder calculations. So, we have the loading on the girder. So, this is the loading, step 1, and then we calculate the resistance of the girder, and there are a few differences that you can see. I will skip just for the sake of time. I can show you the calculations if you are if you want to later on, but the girder itself is given to be, and I wanted to bring a couple of issues to mind. Now, because there is likely to be rebound, so you will have rebound, so pressure coming down and rebound going up. Designs will have steel both at the top and the bottom. So, you should have this is, you might, let us not worry about how we came for this design. We will be seeing some design issues covered. So, let us say this is the dimensions of the girder, this is 28 inches. Where? It is calculated. It is, you can display in non-len. So, for the reaction, the spring force. So, it is a good point. Let us see what the inertial forces are. So, the inertial forces, they start literally almost at the applied load, and so the sum of the two, right, are not exactly, so here it jumps to 118. Yeah. See, the inertial forces, so the reactions, whether it's, if you combine them, the initial one is very high, 118. Is it one? Yeah, it's almost 87, 108 at 0 seconds. Let's hold that discussion. It's a very good point. Let's hold that discussion. We'll discuss something. So, let me just show you what we did. Question is how to consider. Now, the inertial forces are more, the reason at least my logic was, the inertial forces will be at the center of the mass, where, so that is more focused at the center, not at the edges. But I mean, that is something I think if anybody else wants to chime in, you can. But let us keep that. Open. So, let us just proceed with at least what I did. So, then Mn is the same thing for the upward bending. You have to calculate, at least these are the considerations. Upward bending. For upward bending, do not consider again doubly reinforced. It adds to capacity. These are some compromises you have to make. You could if you want to. So to simplify it, the upward, you can say Mn upward is the As Fy for the top multiplied by this distance. Now we consider that you will have the A by 2 right here. So this is your D minus A by 2, assuming at the center. So this is D, or whatever procedure you use, you can consider, but consider only the top steel. So here the area is 7 times 1 square inch, the F dynamic is 77.2 and D minus A prime, let us just take my word in this case for it. So given, and or you can calculate it. So all of this comes to about 8,000 kip inches. And now Rm, now we have, you have 4 loadings in this way. So when you have 4 of them, Rm is now 20 Mn by 3L. So we have seen 8 Mn by 3L, 8 Mn by L, 2 Mn by L. For this case, it would be 20 Mn by. So this comes to, so now I know moment L is equal to 30 feet. So this Rm comes to 130 kips upward. Then we look at downward bending, the normal. So in downward bending, Mn is now As is equal to 6, then Fy dynamic is equal to 77.2, and here for downward bending it is 15.4, because A is going to be different. So comes to 7,013 kip inches. So Rm is now again 20 Mn by 3L. Sorry, this is 148, the other one is 130, I misread. Then the next step is you calculate Ke. Now Ke again, it's a different type of scenario. You have Ke for this loading is 4000 E sub C I average divided by 37 L cubed. And I'll give you these numbers for now, but you have seen all of these calculations. So for concrete, it is typically around 3,600. The I average was based on Ig is equal to 14,744 and I critical is 9768. So this comes to 12,271 and 37 times it is L power 4. It is L power 4 because we are given loads, not a distributed load. So comes to 102 kips per inch. So then your mass is the mass of the beam plus you can consider the ASCE design for petrochemical facilities. It recommends considering 20% mass of skip joists, of the joists. So, you can consider a reasonable mass, and I will just give you the final number here. So, 76.3 pound second square per inch. And the other thing to note again is, that is why we have given you those charts. For a loading such as this, you have KLM elastic, KLM plastic, these are different. KLM elastic is 0.64, KLM plastic is 0.623. This is from Biggs tables, or there are other publications with these tables. So, KLM is also different. If you do not have it, you make some approximations. So, from this, your equivalent mass is 0.631 multiplied by 76.3 kips, or the weight comes to mg, which is 18.6 kips. So, then what I did was I went to non-lin, and so my non-lin parameters were ME, no, the weight was 18.6 kips, and the stiffness was, what was the stiffness? 100 and, for downward, the stiffness was 102 kips per inch. So, you have to take the appropriate stiffness, and let us see what I did. Is that the girder? So, this is the skip joist. So, let us say we finish with this, and then okay. So, this is the roof girder. So, I have taken the stiffness, and this stiffness I have just assumed. You can use 5 or 10, you can change that. The capacity was 130 kips, and then here you have to kind of get creative. So, what I did was to create a triangular loading. You still use a simple pulse, but then I used a ramp time of 70 seconds. That is the only way to create it. You can't use bilinear for this. Created a ramp time of 70. So, now everything is in PSI, but now I do not use a scale factor, and I input a maximum load of, what was the force? 50 how much? 56.2, right? The triangular loading. We did calculate that, 53.4. So, if we, so now I have an area of 1, so now I am going to get 53 kips. So, I am using the same thing. Normally this is done in PSI, so you can convert, you can use the same thing with force also. So, hopefully that's units are all consistent, and then if I use it and run it, so here I get a displacement of 0.767 inches, 0.767, and TM matches 143, it matches quite well. So, now if I look at the different forces, the spring force is 74.22. So, what I get here is from non-lin, the spring force was how much? 76.22, I think. So, this is your reaction, this is, and so that is the peak value, and then you can and if you see further on, this is at about 100 milliseconds. So, 76 point or 70, actually 78 something. So, 78 at so let us say about 78 at 100 milliseconds. And your applied force was, so this is then the reaction, this is on both, okay, no problem, okay. So, you can compare this value, and your displacements is delta dynamic was, if you are looking at the ductilities, the delta dynamic was 0.767 inches. The delta static, this is Rm by Ke, this is 130 kips divided by Ke was 102 kips per inch. So, 130 divided by 2 by 10, how much is this? 130 by 102, 1.3 roughly. So, what we get from these two is it is still an elastic response. So, you can draw some conclusions like this, whether, and the ductility ratio you can find that you see that when we did the elastoplastic analysis, there were dynamic displacements were less than 1, right? Static displacements were something, dynamic displacement were less than 1. So, this is also illustrative of something similar. So, this is one alternate approach. Again, the big question is how to consider the inertial forces. Yeah, I mean the approach I took when you do a single degree of freedom system is Kx is what is transmitted to the supports, M is within the system itself, right. So, it is Kx, your spring force plus your inertial force is equal to the applied force. But oh, I think that's why I was trying not to sit. I don't know what I'll be stepping on. Okay. Anyway, I thought I'll present something and hope you find it helpful. But if you have more better programs, you can actually calculate your dynamic reaction. Remember the shear. Shear is some constant multiplied by the dynamic reaction. This is R as a function of time plus C2 times the P as a function of time. In concrete structures, it's a function of the dynamic reactions plus the applied, or you can, the dynamic reactions you can also put it as a response as a function of time plus the applied force as a function of time. And you will never find them to be synchronous, they're unlikely to be in phase. So, you can use some of the methods, averaging methods, or just take the peak values for design purposes and continue. All right. So let's get back to the impulse quasi-static design based design. So to start with, a summary, what we saw was, if it is an impulse response, what you have is the Rn needed is P naught by RMF, the response modification factor, and RMF was 1 minus 1 over 2 mu, or 2 mu minus 1 by the second one we saw was the quasi-static response. The quasi-static response we saw is given as RMF is equal to square root of 2 mu minus 1 divided by pi Td by Tn. And we saw in case of design versus analysis how to consider each one of them. So in design, let's say you're given a theta max and or a mu max. Typically for RC structures, you would be given theta, typically you're given mu max, and for pre-stressed concrete, both theta max and mu max are given. So depending on the type of structure, you can get it. So if it is simply supported, then the deflection is, it's a plastic hinge formation. So this is theta and this is delta. So you find your mu is equal to your stiffness L divided by, this is basically your delta tan theta max, or the delta divided by L over 2. Now you're finding, but you're given theta max here to find a mu equivalent. So you find your mu equivalent from this expression. And if it is cantilever, here this is theta, and so for a situation like this, your mu is going to be Ke L divided by Rn tangent of theta max. And take the worst of the two mu's. And question is, what about dynamic systems? We found for the static systems, and is a simpler way, there is a way to address that. So if you have a pressure sensitive system, so we saw that it is 2 mu pi Td by Tn. So, this is this was square root of 2 mu minus 1 divided by pi Td by Tn. Wait, I think it's the other way around, right? Let me check. Yeah, this is impulse. Yeah. So, I think let's, yeah, this is impulse and this is the quasi-static. No, wait, this is impulse and this is the quasi-static. So, it's the other way around. So, and then your pressure sensitive was 1 minus 1 over 2 mu. So, the dynamic systems is sort of a mix of these two, is considered in the following way. So, this is a combination of both square root of 2 mu minus 1 by pi Td by Tn plus 1 minus 1 over 2 mu Td by Tn. Now, do not ask me how they came up with this. So, you can consider the RMF used for dynamic systems is something like this. So, so once again let me, so the pressure sensitive systems 1 minus 2 mu, then square root of 2 mu minus 1 pi Dd by Tn, then 1 minus 1 by 2 mu, yeah, Td by Tn plus 0.7. Let me present a couple of notes I had for, in general, for steel structures. We have seen the DIFs recommendations for design are provide lateral bracing for all adequate. So, design it for full capacity. Make sure you are not designing it, what I think there is another term that you use here, right? What is it? I think yesterday you were mentioning it, like Nexi. What are the two designs you? Unrestrained, what's that? Not limit state. Yeah, laterally restrained and laterally unrestrained. It's the same thing out here, we call it laterally braced and laterally unbraced. So basically you are designing it for laterally restrained beam. And if you have a frame, say something like this, just an example, and you might find it challenging to address. There are plastic hinge formations. So, let us say there is a plastic hinge formation, this is a plastic hinge formation here, plastic hinge formation, then there is a plastic hinge formation here and here, and plastic hinge. So, these are, let us say, the plastic hinge locations. You have to decide, and in the courses you have seen how to come up with plastic hinge mechanisms for steel structures, right, plastic design. So, when you calculate, the theta should be less than 2 degrees. So, for overall stability, recommended theta is less than or equal to 2 degrees. This was another point that was raised by Muthuraja, and there was a discussion about it for concrete structures. It's valid for steel. Yesterday's very nice talk. For steel structures also, it is especially valid where your modulus does not change. Suppose you have you can apply the dynamic, although the dynamic increase factors does push it up, but the peak is still considered for design purposes. This is the dynamic stress strain curve, and this is the static stress strain curve. I thought I'll mention this because yesterday's topic addressed a lot of these issues. So, E is constant, or E of steel not affected by strain rate considerations. And I don't know if there's been research for that. There are two philosophies for capacity. The moment capacity is Fy dynamic multiplied by the plastic section modulus plus elastic section. This is for ductility less than 3. This is your plastic section modulus in inches cubed, or modulus is inches cubed, and this is your elastic section modulus in inches cubed. And or if it is fully restrained, Mn is Fy dynamic multiplied by Zx, especially if the duct mu is much greater than 3. Hope I don't topple anything here. So, yesterday's problem, you had a question on what is the remaining moment capacities and all that. So, let's quickly let's address that in this example. Say you have a roof structure these are 4 feet on centers, and this is 18 feet span. These are the beams, a W 12 by 22. So, section properties for a W 12 by 22, Z sub x is 29.3 inches cubed, and the loading applied is dead load is 87 PSF, live load is 20 PSF, and then the blast load is given to be now incident roof walls, back wall, front wall, side walls and back wall, all incident pressures. So 13.9, II is 576. So those are the question is the beam adequate for mu max equal to 12 and theta max equal to 10 degrees based on so this was again based on so today let's see, we had this yeah, no, these are the DIFs. I think I had the LOP's response limits maybe, no, we had the response limits yesterday. Oh, yeah, maximum response limits. So here if you see, this is structural steel, 10 degrees and 12 degrees is heavy. So this is a high level superficial damage, high level of protection. So the capacities that you would use averaging plastic section modulus is for moderate, the high level of protection and medium level of protection. Then heavy damage and hazardous are low level and very low levels of protection we are in. So this is at low levels of protection. So let me add a couple of those. So notes, this is for low level of protection and very low level of protection. I'm sorry, no, this is other way around. For mu less than 3, this is low level of protection and very low level of protection. So in our case, we have, this is medium level of protection. So let me insert that anyway. Which I think it was, no, not this. How do you delete? Okay. Okay. So what you see here, this is structural steel, heavy, this is medium level of protection. So, first step is calculate applied loads. Same procedures, and so start with our dead load. The dead load, let us say PD is 87 pounds per square foot multiplied by 4 feet. So, this is 0.348 kips per foot. PL is 0.02, again tributary width 4 feet, and so this is live. And finally, the blast is PI, P naught is PI multiplied by the tributary area. So, this is 13.9 multiplied by, the span is 18 feet and tributary width is 4. So, comes to 144 kips. Then next step is we calculate the design capacity. So, SIF equal to 1.1, the DIF is 1.19 flexure. So, Fy dynamic is SIF. So, the work he presented is helpful for mostly yesterday Mutturaj presented. You can use it for design purposes for UHPC, mostly applicable for design. It is a little bit harder to implement it for finite element models, some of that information. This is because there is a lot of extrapolation that is involved. We will maybe address a little of those issues on Friday. So, comes to, this is 50 KSI, comes to 65.5 KSI. So, then the beam, we would make sure you laterally support it. So, is laterally restrained. So, My and mu is greater than 3. So, you have MP is Fy Zx. So, this is 65.5 multiplied by 29.3 divided by 12 is 160 foot kips. Then third step is we calculate now the remaining moment capacity. This is what you had not done yesterday, but you can see, you can add that in the problems. So, in the remaining moment capacity, M and Rm is Mn minus Mu for dead load plus Mu for the live load. So, let us calculate in US load combination, ASCE load combination, let us say. So, the ASCE and Indian load combinations could be, I knew it once upon a time. I have done a bunch of building designs, but back in the 80s. So, I've forgotten those combinations. So, for blast, it is relatively recent, as I said, in the last 10-15 years, this combination has been introduced. So, we use roof live loads are much lower. So, this comes to 1.2 times 0.348 plus 1.2 times your dead load. This is your self weight plus 0.5 times 0.08. So, the overall is 0.484 kips per foot, and so W live load is sorry, M sub U is WU, L is 18 feet, comes to 19.6 foot kips. So, Mn Rm is Mn multiplied by M sub U. So, this is 160 minus. So, now you might ask, why would you design a beam that needs only 19.6 foot kips? But remember, you are designing for 1 point, in US for regular live loads, this factor (1.6). So, so in these designs, once you design for regular dead loads and live loads, you could provide additional capacity to. So, keep an eye on this. It's a small percentage here, but that is what we would be using. Then we calculate the Rn, and Rn is 8. Now, Mn Rm divided by L. So, 8 times 140.4 divided by 18 feet. So, value is 62.4 kips. Rn by delta. So, we have this is y sub e, y sub m, the max value is 62.4 kips. This is our resistance curve. So, every time I think if you are working in areas of research, these are some things. Yesterday's talk also brings to light many of the difficulties. You should think of reporting strain rate if possible, especially concrete or masonry or anything like that, your load deflection response itself is a resistance curve. So anything you can add to literature when you report it, report the response as a resistance curve for that specific applications, and see if you can generalize or recommend a resistance curve for similar structures. If you're writing a paper, this is for mostly for addressing research people, add a section. It would be very helpful for somebody like me to add, or anybody, designers especially, to add a section on how this can be extended to other similar types of structures that you are researching on. So step 5 now, or step 4 rather. So the dynamic footprint of the system. Starting with the mass. The mass is basically your KLM multiplied by W dead load plus W self weight multiplied by L divided. So this is your G. Now KLM for this system is 0.78. So comes to 0.78 times 0.348 plus 0.022. This is in kips per foot, divided by 386 multiplied by 18 feet. So here this is kips per foot, you don't need to do anything else, and divided. So this is in kips, so multiplied by 1000. So comes to 13.45. KE is 384 EI by 5L cubed, and for a W 12 by 22, I is 154. E is 29,000, and so E is 29,000 KSI. Here is what 210 GPa, is that gigapascals? 210. Okay. So L is equal to 18 feet. So this value comes to 34.47 kips per inch. And the natural time period to pi is 0.124 seconds or 124 milliseconds. Sorry, milliseconds. Right? So the properties that we need are M and K and Tn. Can you just give me the weight also, please? We do 0.348, or just multiply 13.45 by 386 divided by 1000. 5.19. Thank you. So the next step is the roof response. There are a couple of ways of doing it. So we'll start with TD by Tn, which is (8.3 milliseconds by 124 milliseconds). So this is 0.067, which is less than 1. So yesterday I showed you an impulse equation. You can use that I square A divided by Km, right? I square A by Km equal to the Rmxe and xm minus xe. So you can use 1/2 or you can use several ways. You now have several ways of doing it. We can compare actually. Maybe this afternoon that could be one thing we can try. So it's an impulsive response. The second thing is we are given mu equal to 12 and theta equal to 10. We find the equivalent mu for theta equal to 10. This is basically x static, the equation that we've shown here, Ke L divided by 2 Rn tangent of theta max. So 34.47 18 divided by 2 times 62.4 kips not per inch multiplied by tangent of 10 degrees gives you so you have a choice of 12 or 10. So limit it to the lower one. So in steel you will find, pre-stressed concrete and others you will find this option. Then third is calculate RMF. It's dynamic, impulse. So RMF is equal to square root of 2 mu minus 1 divided by pi. So 2 times TD is this whole thing is 0.067. Now, this is why I say do not equate it to seismic RMFs. Here RMF is anything, we calculate an RMF, the response modification factor. It's, I think they should have called it something else, or we can call it something else. Because seismic, you're limited, that those are all fixed quantities based on the level of ductility that is desired. If you are low ductile like masonry, then you may be RMF of 1.52. Concrete you might start getting 2 to 4. Steel, depending on the type of moment frames, whether you have intermediate moment frames or there are levels of moment frames. Highly ductile moment frames versus less ductile moment frames, you have going from 4 to 8 or more. So different structures have different RMFs, that is fixed. So you go to just like LOPs, you go to a table, you pick the RMF intermediate moment frame, then you pick the RMF for that design for it. But here you calculate the value. So that's the difference. Then check the required strength. Your F required is P naught by RMF. Your applied, it's kind of sometimes scary to see that your applied force is 144 kips, but all you require is 1/20th of it. Sometimes these values, RMF, artificial RMF, these values come to be very high, especially if you're coming from a seismic world. This can be really, really hard to accept. So the Rn provided is 62.4, so this is adequate. For medium, it could perhaps even be providing much higher. I don't know, this afternoon I think we can try using that impulse equations that we presented yesterday, right? Let's try that on this, and I don't have that comparison, but we'll finish with a nonlinear check is I don't know if I have this. So the weight that you calculated, how much? 5 point, you said? 5.6 you said? Or 5.19. So this is 5.19 kips. Then damping, let's say steel could be higher, but let's just try different damping ratios. Don't go anything beyond 10, even that is high. Then your stiffness is K 34.47. Then 3 point, let's say nonlinear analysis. I think we got all of this here. Time period 124, that's fine. And then we are applying 13, pulse duration is 8.3. Pulse itself is 13.9. The area is 10368, tributary area. Scale, no, this is 0.0139. No, 0, yeah. You can put 13.9 and put a scale factor of 0.001, whichever works. So plot, we use this. We're missing the strength. The strength is 62.4. The displacement seems to be very high. 13. Can you check the area, please? I don't know if the area is too high. Area is 4 times 30 times 144. I think that's okay. Oh, ramp time. Oh, we have a ramp time. Yeah, that makes sense. So we get as a comparison, I've done Rm by F naught is 62.4 divided by 144 kips, which is 0.43. This is charts. And Td by Tn is 0.067. So from here I get delta dynamic by delta static is 0.8. Delta static is Rm by Ke, which is 62.4 divided by 34.5, which is 1.8 inches. So therefore, delta dynamic is 0.8 times 1.8, which is, so we are a little bit off. So multiple ways of doing and designing.